So let's actually copy the history we started last lecture and make a script of repeating experiment. All right. So the first step of the experiment is what? In a Monte Carlo method, what do we start? Generating the random samples, exactly. So we are going to generate the random samples, and last lecture we used the acceptance rejection method, right? So we started by sampling a bunch of random numbers, and
we decide the number of samples is for the acceptance rejection method.
How do I? Yeah, so that's a good question. That's what we are going to learn today. Is how many samples are enough? So, for example, you give me a range of probability from 1% to 2%, and I'm gonna ask you what is the confidence, and you're gonna give me a confidence level, right? Maybe you're saying I'm 99% sure, and then potentially this answer is not satisfactory. Perhaps I want the probability to be narrower, right? Between 1 and 2% is not enough for the kind of purpose I want to make decision. So you have to shrink your confidence interval, or maybe 99% is not enough. I want 99.9%. Then either these two cases, you need to find a way to be more confident about the answer you are giving. So over here, like one of the primary source of uncertainty is because of the finite number of samples you are using here. So here we are also going to study, as we increase the sample, how is our confidence improving, right? So that's one of the questions we're actually going to study today. So here, for the purpose of answering that question, where do we actually want to make n samples to be a variable. So let's start with something, let's say 100,000, okay? And we are going to copy this, and we have dv, and we also get to the t, right? So let's paste over here and change this to n samples. So we make a bunch of uniform random variables. We transform it to the desired interval, and we compute the probability of acceptance based on where x lies. Don't plot it, and then we sample an independent set of random variables to decide if I want to accept or reject each sample, right? So I accept is now decided. Am I going to accept or reject? So I'm going to compute x try. So let's directly set my delta v to be this. And then I have an independent set of runs to compute my t, right? Okay, so these are the two set of random samples I'm going to use. So then my ultimate number of samples so actually this n sample is n proposed samples, right? Because some of them are going to be rejected. So I'm going to post it over here. And the real number of samples is going to be the minimum of length of dv and the length of t, right? So that's actually how many samples I get. So dv is going to be dv 1 to n samples. T is going to be t 1 to n samples. Now I get a real set of n samples where I can start my simulation. Okay, so then the next is I need to actually call this function, right? So I'm going to say, okay, so if I start this, I'm going to compute probability equal to crash the dv and t, right? So now I compute the probability with a fixed, let's say x0 equal to 50 kilometers. I'm going to compute the probability. So let's run it to see if we actually get anything. Actually, no. Undefined function. Okay, so it's a small v, right? Yeah. Let's run it again. Yeah, we compute the probability 30.13%. Now, how confident are we with the number? Let's actually run it again. Run it again. We get a number that is slightly different, 30.36. We can now run it yet again, 30.60. So repeating this experiment actually gives us a certain level of information on how variable the number is. The more variable the number is, the less confident we are with our result, right? So, and we can also see if we start with a less number of samples, let's say if go to the extreme, let's start with 10 samples, we are going to get very variable results. So this we get 25%, we get 42%, we get 25%. So there is a lot of variation in the result we get. So with a small number of samples, we are less confident. With a million samples, for example, we are probably going to be more confident. Every time we compute this, the variation is very small, right? So one of the method, the brute force method, is to actually repeat your Monte Carlo method for many, many times and collect the statistics of, for example, if I repeat it for 100 times, then I can simply say that my 95% confidence interval is the, for example, it's basically excluding the largest 2.5% and excluding the lowest 2.5%. And the remaining data set, the upper and lower bound of the remaining probabilities is my confidence interval, 95% confidence interval. Right? Does it make sense, this approach? I'm going to compute, let's say, 1,000 p's. I'm going to exclude the largest 25 once I compute, exclude the lowest 25 once I compute, the middle 950 ounces, I take the minimum and maximum, and that's my confidence interval. So what's the problem about this approach?
Because you have to run the simulation.
It's very expensive, that's right. It's very expensive. So how many times I have to run the simulation if I use 1 million samples for each calculation and I have to repeat the calculation for 1,000 times? 1,000, I mean 1 billion, right? So I have to run the simulation 1 billion times. In this case, it might be okay because my simulation is actually very simple. But imagine if your simulation actually involves something that that involves solving a PDE, for example. Then it's very hard to imagine actually running 1 billion simulations just to get a confidence interval, right? So the method we have been using is actually not a brute force method. The method we have been using is actually very clever. It takes a central theorem in probability called the central limit theorem.